Hello, everybody. Thank you for watching. Today, we would like to learn about the HQ equation or HQ check basic theory from the Bernoulli principle. So, if you know detail about the theoretical background, then you can know more what you have to do as the field, and it will be the good observation. So let's study a little, and I prepared some slide that I used at the classroom. So wait a moment, I will show the slide here. It's okay. Can you see? Okay. So the title is HQ qualification theoretical background from the Bernoulli principle. Okay. Not so difficult. So this is the Bernoulli principle, and this is a kind of the energy energy conservation law. So you mean that I know you know that this shows the some velocity energy from the movement and the pressure and the position itself, gravitational position. So that is the energy, potential energy or pressure energy and moving energy, and summation of them is constant. This is the Bernoulli's equation, Bernoulli's principles. So this is a little bit not a good picture, but you can see that the some point number 1 and point number 2, and there is some big base and some hole here, and number 1 and number 2 has the same system in the same system. So the total energy of number 1 and total energy of number 2 is equal. That is Bernoulli's principle. And be careful that the number 1 is the some stable point, and the number 2 is not stable, but there's some velocity. You know, you have some water velocity here. So, but this is the atmospheric, that is atmospheric pressure is zero, not in the water, and not negative pressure. Negative means some suction force, but this is just the water phase surface. And number 2 is a little bit different, but this is open to the atmosphere. So number 2's pressure is 0, and the number 1 pressure is 0. That is the same atmosphere pressure. And for the easy understanding, the position is set at 0 at the height of the number 2. So number 1's height is h, and the number 2 height is 0, like this. And you know that the velocity at number 1 is water velocity. Number 1 is 0, and we do not know the water current velocity at number 2, so it's V. And then Bernoulli saying that the number 1 and the number 2 is equal, so you can calculate like this. Velocity at the number 2 is just like that. Velocity is decided with the water depth. Okay, and then this is a sample of the rectangle weir, and how to calculate the rectangle weir with height. So you can check at the height h, it's the water depth is h1 minus h. This is the water depth. So we can say the velocity at the height h is like this, and the width of this rectangle over here is large b. So we can integrate the total runoff rate like this. Okay, so the calculation method of this integral is a little bit difficult, so we have to change the parameters like this. Then we can calculate the rectangle here, h and q, height and quantum water velocity amount with this like this. Okay, and this is a this is a slide of that at my classroom, so report. But you can see that wait a moment, at the rectangle where the water amount, water velocity, water flow is determined with the uh, overflow height and the power of the 1.5 rectangle. And at the triangle, this is you can calculate like rectangle here with the triangle here, and that is a student's report here, and the summary is like this. So water flow. Water flow means cubic meter per second. It's determined with the water height, and the power is 2.5 here. And you can calculate some parameters like here, but it is some report like this. And be careful that the parameter C is not the integration constant, but this is shrinking coefficient or reduction coefficient of the water flow. So that means this one. So you know that some water flow at weir is not stable. For example, at the weir, the height of the water will be reduced. And this is, for example, this is velocity is zero velocity, but this has some velocity, and we can calculate with some integration with triangle or rectangle. But this is a very important point that the overflow height is not A, but B. So this picture is showing that a student read the water gauge level here. So can you see that we set the water gauge level here? So a student have to read this. So even that can you see? And at the V where and the water is running here. So you think that the water is running at the V triangle here. You think it is easy to measure the water height here, but it is not good because water is shrinking like this, reduction of the water. So not this value is the overflow height, but we have to check the point at somewhere at the background of the pool, and the velocity is zero. So here we set the water gauge here, and he read the water gauge at there. Okay. So then we can show some application of the HQ equation. For example, here, this is the at the Borneo Island, Rambil Hills National Park, and I once observed the runoff here. But we would like to make some weir here, but we cannot make them. So I check the water height, the shape of this cross section, and at the river. Then I check the water flow with propeller, current meter, current velocity meter. So I make the HQ curve with the shape of the riverbed, and if we can check the shape of the riverbed, and checking this weirs with the height, then we can calculate the hydraulic equation of the HQ. It's this line is HQ, and I also observed with the propeller current meter, and then this shows that this hydraulic curve with Bernoulli principle is equal to the observation. So we can use this curve and the water height and the discharge rate. So if we can check the river shape, that means FH here, then we can calculate the HQ equation. And another application is here. Sorry. This is some Excel worksheet, and this is made at the Roth mountain at the VNUF watershed, and this shows some multiple shape weir. So if the water height, oh sorry, I can't write here. So this is kind of the multiple shape. This is some with the free area and the rectangle area. So if the water height is here, this is just like the triangle here. But if the water height is here, then this is some multiple shape watershed. But in this Excel worksheet, we can calculate like this. If the water height is 0.3, then it's very difficult equation like this. But this is numerical one, reduction coefficient and degree of the angle theta, and H1 is some kind of number, and B is the width, and Z is the gravity one, and we can calculate with very long formulation, but we can calculate with some multiple shape weir too, and this show that if this height is larger than H1 or not, then this calculation switches this equation and this equation. And if you change this type of the weir angle, for example, 60 degree, then the HQ curves are changed a little. So this is some application. Okay, so if you know the theory of the okay, so if you know the principle and the theory and the background of the HQ equation, you can know more about the HQ observation. So please do the precise observation at the weir. Thank you. よいしょ。こうか。